In this video, we'll talk about inductance. Here I have two loops, loop 1 and loop 2, and I will think about having a current flowing in loop 1. So this is I1. I know that the current in loop 1 will create a magnetic field at the location of loop 2. So this will be the magnetic field that current 1 creates at the location of loop 2. And because I have a magnetic field at the location of loop 2, I know that this will give me a flux at the location of loop 2. This is the flux that goes through loop 2. Now, I know, okay, this is the definition of flux. So we're dealing with magnetic flux. This is the surface integral of B, the magnetic field that the current in loop 1 creates at the location of loop 2 dot dA2, and this is the integral over the surface area of loop 2. Now we know Biot-Savart's law, right? Mu naught 4 pi I delta L cross r hat divided by r squared. Let's make that to be a small delta B from a small current. Okay, from Biot-Savart's law, we know that the magnetic field will be proportional. The magnetic field that current 1 creates at the location of loop 2 will be, okay, the strength. I'm only discussing the strength. The strength of this will be proportional to current 1. And if I think about including a magnetic field here in the calculation in the flux that is proportional to current 1, then that means that the magnetic flux that goes through loop 2 will be proportional. If I take these two, that means the magnetic flux that goes through loop 2 will be proportional to the current in loop 1. Now we call that constant of proportionality is what we call the mutual inductance. And this is a geometric quantity. This depends on the geometry of the two loops. And in fact, you can show, I will write with different font color. You can show that this constant proportionality can be calculated in general as mu naught over 4 pi, and those are two closed path integrals. These are over loop 1 and loop 2, dl1 dot dl2 divided by r. So this is the what we call the mutual induction, and this is the mutual inductance. Now, of course, if I do the opposite, if I have a current flowing through loop 2, there will be a flux that goes through loop 1, and then I could say the flux through loop 1 is the mutual inductance times the current in loop 2. The M here and the M here are the same because, remember, this mutual inductance depends on the geometry. So long as you keep the geometry the same, it doesn't really matter which one you call 1 and which one you call 2. The mutual inductance will be the same number in the two cases. And if you know the mutual inductance, this allows you to go easier from the current in one loop to the flux in the other loop. If you remember, when we work on problems with Faraday's law, we do have to follow a fairly long thinking process from the current. I have to find B, and then I have to calculate the flux and then the change in flux and so on. Sometimes you may need to think about the change in B if you want to use Lenz's rule. In any case, this is, if you know the mutual inductance, it makes things a little bit easier when you use Faraday's law for in that system. It just makes things a little bit easier. But you don't have the mutual inductance in all cases. Sometimes you have to calculate it. If it is given to you, then great, go ahead and use it, but we don't always have access to that. And I do want to show you, if we do have the mutual inductance and this allows us to find, let's say, the flux through loop 2, when you apply Faraday's law, then we have the induced EMF on loop 2 will be minus dphi 2 over dt, and this becomes minus d over dt of m times I1. And because the mutual inductance is independent of time, this will give me minus m times d I1 over dt. So this is how you can use this expression using the mutual inductance in Faraday's law. And actually, this expression showed you explicitly something that we've seen in problems before. It is the rate of change of the current in loop 1 that dictates the size of the induced EMF in the other loop. Okay. If I give you, for example, a graph of the current in loop 1 as a function of time, you need to find the slope or the negative slope of that to determine what is the size of the induced EMF on the other loop. Okay, it's the slope, it's the rate of change of the current here that shows you how strong the induced EMF on the other loop will be.